January 2025, Section C, question number 20. Oxalic acid has the IUPAC name, ethane dioic acid, and a molar mass of 90 grams per mole. Okay. The name oxalic acid originated from the fact that it was first isolated. Okay, 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 okay. What the question they are asking, calculate the atom economy. The main question that they are asking, calculate the atom economy by mass for the formation of oxalic acid from the hydrolysis of 2-oxo-butane dioic acid. What I will do, what's the formula for percentage atom economy? Like, what's the formula for atom economy by mass? So they are saying formation of oxalic acid. This is going to be oxalic acid. So what I would do, I would take the mass of oxalic acid, let me write down the formula. Mass of oxalic acid divided by, okay, divided by the total mass of the reactant, the total mass of the reactant, right, multiplied by 100. So oxalic acid they have given, I think so. Yeah, it was 90. So 90 over over the reactant side. This is going to be your reactant side, right? And I need to find out the MR of this reactant side. Sadaf, can you tell me the molecular mass of the reactant side? Yes. The molecular mass of the reactant side. Let's say it would be C, then C, then C, then C. 4C, and then we have CH2. Then you are supposed to count the total number of hydrogens. Then you are supposed to count the total number of oxygens. Then you have to see the atomic masses from the periodic table. Then you have to add them together so that I can divide and I would be getting the answer. Uh, what I have calculated is 132. Are you getting the same answer? And of
Yes,
course,
sir.
water is 18. So 132 plus 18 is going to be the total mass of the reactant side and multiplied by 100. So what's the answer?
Sir, it's 60%.
Okay. Then part B says, give the laboratory reagents and conditions required to convert glycolic acid to oxalic acid. Do not consider nitric acid. So this is called glycolic acid and this is called oxalic acid. What I'm seeing is that it's a carboxylic acid. It's a carboxylic acid, it's a carboxylic acid. It's a carboxylic acid. So, so I would say that, what they are saying? Laboratory reagents and conditions required to convert glycolic acid. Oh, okay, okay, okay. Let me write it down. COH and CH2, and then I have C double bond OH. This is alcohol. And in oxalic acid, two carboxylic acids. So what I have to do, I have to convert, I have to convert alcohol into carboxylic acid. I need an oxidizing agent. I need an oxidizing agent. So what I would do, I would be writing that I need K2CR2O7 plus sulfuric acid, and heat under, and and heat under reflux. When I will be adding these reagents and conditions, so the primary alcohol would be converting into the carboxylic acid. And yes, I would say that I have prepared oxalic acid from uh, glycolic acid. Okay. Sucrose is oxidized by concentrated nitric acid to form oxalic acid. Complete the equation for the reaction of 1 mole of sucrose with nitric acid. So, oh my God, 36 nitric acid. Okay. So I need to balance this equation. What I would say, NO2. So of course, NO2 would be 36. To balance nitrogen, it should be 36. And how many hydrogens I have? 36 and then 22. It's gonna be 23 into 2, of course. That is going to be 46, right? Or then I have 12 carbon atoms. It has one, then two. Two carbon atoms. Two carbon atoms, so it's gonna be six, so that it may become 6 to the 12, because on the right, on the left hand side, you have 12 carbon atoms. This is your balanced equation. Give one observation that would be seen during this reaction. Of course, you can see NO2 gas is produced. You know what would we observe whenever I have NO2 gas? So I would say that reddish brown fumes. I would say that reddish brown fumes of NO2 would be observed. Now, it's a titration curve. If you remember, we have discussed the four types of curve, strong acid versus strong base, like that. So a solution of sodium hydroxide was titrated against 25 centimeter cube of oxalic acid solution. Both solutions were of equal concentration. A student is sketched a curve to show the changing pH during the titration. Okay, select one indicator for each equivalence point from this titration graph. Include the color at the end point for each indicator. Use your data booklet. So, how can I select an indicator? I told you that this is your pH range. I would see whose range would be in between 3 and 4.5, right? 3 to 4.5, and then it's a larger range. Okay, it's a good. That's good. If we have a larger range, we can select multiple indicators. It's gonna be from 6.5 to 12. It's a larger range, right? So what I would say, I can say that like from the beginning, it's the first indicator that I can select is going to be you can say they are saying only one indicator, right? Select one indicator, right? Okay. So I can say that it's gonna be methyl orange. I can say that it's gonna be methyl orange. Okay. And color at the end point. Color at the end point, right? So what we have taken in the burette and what is in the conical flask, volume of NaOH added. What do you mean by this? In that NaOH is present in the burette. NaOH is present in the burette. Okay. So, uh, yes, yes. So, first indicator is methyl orange. So, in the end, there will be extra base. So, methyl orange is yellow in the presence of base, right? It would be yellow, by the way. And then, second indicator, we have a larger range. So, I can say it's gonna
Can
be
we use
phenolphthalein.
phenolphthalein?
Sorry,
I was just gonna ask, can we use phenolphthalein?
how can we what?
No, I was just gonna ask, can we use phenolphthalein?
Yeah, exactly. The one, the one which would lie in between this range, in between this range would be the most suitable indicator for this titration. It may be anything else. So I can use phenolphthalein for the second titration, you know. Phenolphthalein is a pink in the presence of base, and phenolphthalein is colorless in the presence of acid. Phenolphthalein is pink in the presence of base, and phenolphthalein is colorless in the presence of acid. Remember, okay? So what I would say, color at the end point would be pink. Color in the end point would be, I can say pink, right? So suggest a difficulty that would occur if both indicators were present in the same mixture. The thing is that they are different indicators. If the indicators are present in the same mixture having the different colors, so it would difficult to see the color. It would be difficult to measure, to observe the color, because you know they are having this different colors and they are present in the same mixture. So difficulties, of course. So to observe the color, to observe different color in the same mixture. Determine by using the graph the two Ka values for oxalic acid. You must show your working on the graph. Ka values, right? So how can I select? How can I select the Ka values? And you have to select the two Ka
half
values, by the way.
equivalence point and then half it again.
What are you saying, Roma?
We can find the half equivalence point for the both graphs and then we can half them again. And then the pH will be equal to the pKa value.
Yes, pH is equal to yes. Okay, you're saying right. So, okay, I'm doing working. You can see over there, right? So when you will be having a hard copy of this paper, you can solve it by yourself. So I can say that uh, pH is equal to pKa. You know, pH is equal to pKa. It's called half equivalence point, right? pH is equal to pKa. It's called half equivalence point. Okay. So I can say that this is your half. Okay. What's the volume? What's the volume? You know, can you tell me the volume? And also, this is the volume. By the way, this is also the volume, right?
25.
So what is this? It's 25, right? So it's 25, okay, and it's gonna be 50. And it's gonna be 50. So 25 plus 50 divided by 2 to get an average. What's the answer? 25, 20 plus 50 divided by 2. Yep,
37.5.
37.5, right? Okay. And also, if you can see this one, when the line becomes straight like that, and also this one, it's gonna be 4.4. Okay, I got the two values, and then I would be getting, I can say that it's gonna be like that, and another one, I would say that this is going to be like that. So we have to get the two numbers, right? We have to get the two numbers. So, okay, then half of this one, half of this one. Yes. Can you tell me now what am I supposed to do? Now I can,
We
I'm
divide
going to do a working over
37.5 by
there.
2.
Yeah. First, I'm saying that first KA, first KA. Then I can say that it would be second KA. So for the first KA, I would say that pH is equal to pKa, right? So negative log of A is equal to, yes, is equal to, now which value I am supposed to take, right? Which value I am supposed to take. So it's gonna be over there. It's going to be 1.3. So I would say that negative log of K uh, is equal to 1.3, and then it's gonna be Ka is equal to 0.050. It's the first equivalence point. Then what can I say for the second one? Again, the same thing. I would say that pH is equal to pKa and negative log of Ka. So I would say that it's gonna be like that, like that, around 5.3. So 5.3, it's gonna be 3.72 10 raised to the power minus 6. It's the next equivalence point. It's Ka. It's what? It's Ka, right? So it's of 5 marks, so you have to do working. Spinach is one plant source of oxalic acid. Approximately 700 grams of milligrams of oxalic acid can be extracted from 100 gram of spinach. High performance HPLC, high pressure liquid chromatography, is used for analysis in the extraction process. The HPLC equipment is connected to a detector which record peaks when substances pass through the HPLC column. Suggest how a pure sample of oxalic acid would be used to identify the oxalic acid peak in the chromatogram of the spinach extract. Okay. So basically, using chromatography, it's a separation technique. Not only the separation technique, not only the separation technique, but also, it's a purification technique as well, right? Also, it's a purification technique as well. So they are saying HPLC is used for analysis in the extraction process. The HPLC equipment is connected to detector which records the peak when substance pass through. Suggest how a pure sample of oxalic acid would be used to identify the oxalic acid in the chromatogram. So, what I would take pure oxalic acid. and then I would be finding out the RF value. I would be finding out the RF value. It's of only 1 mark. It's enough to write. It's enough to write that find find RF, find RF, or I can say not RF. RF is used for the column chromatography, like paper chromatography. It's basically retention time. Find retention time. Find retention time. Okay. Uh, of the pure sample of oxalic acid. Pure sample of oxalic acid, right? Then it's of 3 marks. It's of 3 marks. They are asking uh, calculate the mass of spinach. Calculate the mass of spinach required to make 500 cm cube of the oxalic acid cleaning solution. Yes. And they have given you the concentration of oxalic acid as well, by the way. And they have given you the moles volume of oxalic acid as well, right? So what I would do, uh, I can find out the moles of acid, mole of oxalic acid, concentration multiplied by volume. Concentration multiplied by volume. Yes. What's the answer for the moles? Yeah.
0.279.
0.279. Okay. So 0.279 is the mole of oxalic acid, right? And I have to find out the mass. It's gonna be mole multiplied by MR is given, that is 90. So what's the answer for the mass?
It is 25.11.
25.11 grams. Okay. And afterwards, I can say that what they were saying in the question, spinach is one plant source of oxalic acid. 700 milligram of oxalic acid can be extracted from 100 gram of spinach. So I can make an assumption. 100 gram of spinach is used to extract 700 milligram of oxalic acid has been obtained. Okay, so 700 milligram, or I can say 10 raised to the power. So let's say if I'm going to do a calculation for 1 gram, so in 1 gram, this is gonna be Yes. What's the answer? Per 1 gram, right? That's why I'm dividing it.
It's 1.43 times 10 to the power of minus 4. 1.43 times 10 to the power of minus 4.
Okay, I'm sharing my screen. 1.43 exponent minus 4, right?
Yes.
Multiplied by the mass that I got in this one. What's the answer?
Sir, I didn't understand why you did the last part.
Basically, they were saying calculate the mass of spinach required to make 500 cm cube of the oxalic acid, right? 500 cm cube oxalic acid, or else I can also do in this manner. You can see you can see over there. Let's say first of all um, I'm going to find out the concentration of oxalic acid, but in grams per decimeter cube, right? So it's gonna be uh, how much moles I got? How much moles I got? Yeah, okay. Concentration is given 0.558 mole per decimeter cube. When I would be multiplying this with the MR of oxalic acid, which is 90, I would be getting the concentration in grams per decimeter cube. In grams per decimeter cube. That is 50.22. That is 50.22. Remember, now what I'm going to do, I'm going to find out the mass of oxalic acid in 500 centimeter cube. In 500 centimeter cube, how? How? It's 50.22 grams per decimeter cube multiplied by 500 10 to the power minus 3 to convert it into the decimeter cube. So when you will be multiplying it, you will be getting the mass. That is going to be 25.11 grams. That is going to be 25.11 grams, right? Now, what I'm going to do, I'm going to calculate the mass of spinach. I'm going to calculate the mass of spinach. For the spinach one, what I'm going to do, 25.11, okay, 25.11 divided by its milligrams. I'm going to convert it into the grams. 25.11 divided by 0.700 and multiplied by 100. What's the answer for this one to get the mass of spinach? Yes.
It's 3,587.
Grams. That's your answer. Because they were saying that in 100 gram of spinach, this much oxalic acid is produced. In 100 gram of spinach, this much 0.700 gram of oxalic acid is produced, right? Oxalic acid is produced. If I have this much oxalic acid, how much spinach is produced? What I did, I just cross multiplied it. You can see over there. I got the mass of spinach. isn't it? Right? Are you
Yes.
getting my point? Yes. Right. Write the
Yes.
equation for the reaction of oxalic acid with excess phosphoric as phosphorus chloride. Basically, you know what the phosphorus chloride would do? What the phosphorus chloride would do, the phosphorus chloride would be substituting. The phosphorus chloride would be substituting the OH from the carboxylic acid and the chlorine would attach. So I can say that oxalic acid is this one. Okay, it's oxalic acid. It's going to react PCl5. So the same structure but with Cl. The same structure but with Cl, and along with this I have to form PoCl3 and H2O, HCl I can say. So this is your chemical equation. Should be balanced. Oh, it's 2, 2, and then hydrogen is also not balanced. Yeah, now this is balanced chemical equation. Okay, so